Okay, let's get started. Uh, Before I start today, I want to take any questions you guys might have. As you know, this is the final week of instruction. One quick point about the homework. I just heard that Al sent out a correction to homework assignment. So if you didn't get that email, make sure you talk to Al about that. It's also good that you make sure you're on his email list. If you're not on his email list by now, you're probably doing something wrong. Okay, any questions about the project? Good question. I was planning on having it due at the latest at the final, but hopefully you guys won't push it that long. I'm sure you have better things to do than spend your final week working on the project. But I want to give you guys the maximum amount of time that possible. Just curious, how many people are done with the project, or pretty close? They feel pretty good. Am I the only one who's done? How many people haven't even started?
Haven't started?
Yeah. Okay. I saw one hand kind of go up and then come down. Maybe it's a little bit too embarrassing. How many people feel like they're halfway done? They've made good progress. They're pretty happy. No, nobody's halfway done. Maybe one person. Okay. All right.
Well, whenever you think you're halfway done, you realize, well, there's a lot more.
That's true. That's true. Okay. Feel free to come to office hours to talk to me about the class or the project. This week we'll have regular office hours Wednesday, Thursday, and if you can't see me during those times, feel free to comment. Send me an email and make an appointment. Question?
For the project, you have given us to calculate the noise figure over a range, some 1 kilohertz to 1 megahertz bandwidth.
That's
so,
right.
the noise figure, we have to get the output noise, integrate it, and then divide by what? How do we know what's the...
You assume you have a certain signal power coming in over that same bandwidth, so that's what you divide by.
4 kTR into that bandwidth is the input noise power.
So using the definition of noise figure, so it's the signal noise ratio at the output divided by signal noise at the input. SNR at the input is well-known quantity, right? So SNR at the output, to find the noise at the output, you integrate over this bandwidth to get the total noise power. And then the signal power is the power gain of your device times the input power, which will cancel out, right? Okay. Another question?
For the LO signal, can we assume a square wave, or it has to be a sinusoidal signal?
You can assume a square wave, but you have to include the power of that square wave, the power to drive your mixer in your total power budget.
And for the LO, can we assume a differential LO is available?
Okay, you can assume a differential LO is available, but again, make sure you calculate the power appropriately. Okay, I could see this discussion running away into a discussion about the project. Keep it short, keep it simple. Don't make it fancy. It's not worth your time or my time. I basically want to see your schematics, explanation, simplified schematics. Don't print out ugly, Cadence Spectre kind of schematics. Simplified schematics. Describe how the circuit works. Describe each block, how it works, what specs you achieved. Explain your simulation results. You can just print out your simulation results and write on them. So it doesn't have to be any kind of specified format. The results are more important than your, it's not an English class, right? Not a writing class. Anything else? Yeah, so if you...
What if we can't achieve one of those specs?
That's fine, right? That's okay.
Explain one.
Yeah, that's fine. And, if you have more questions about the project, please come to office hours. We can talk about them more. All right. Also, as far as the final goes, I'm going to pass out, or I'll post the final exam from last year on the website. You guys can look through that, and that'll be a sample final exam. All right. Anything else?
Next lecture is going to be instruction lecture, or are you going to be solving the
No, next lecture will also be instruction.
Is there going to be kind of like special session where we're going to be solving the...
You can come to office hours if you have questions about the exam. Yeah.
Is the final course not supposed to
Yeah, it'll be closed notes. Actually, that's it doesn't. Yeah, it can be open notes. You shouldn't need them, but it should be open notes. If you're searching through your notes, you're in trouble. Also, as far as what to expect on the final, of course, the last year's final is somewhat representative, but as a general comment, the final is going to be somewhere between lecture and homework. So homework has been pretty difficult this semester, so if you understand all the homeworks, you will ace the final, basically, no doubt. If you're having trouble with the homeworks, but you totally understand the lectures, I think you're also going to be in good shape. You're going to ace the final. If you don't understand the lectures, you're going to be in trouble, okay? And some lectures will be weighed more heavily than others. So sometimes we veer off into more advanced topics. I'm going to emphasize the advanced topics much less. So for instance, did a whole lecture on phase noise. That is to give you guys some insight into what's going on, but I'm not going to ask you difficult phase noise questions. I may ask a simple question that you could work out on in one page with algebra, but I won't ask you guys to derive an ISF for a nonlinear oscillator or something like that. Okay?
Well, excuse me, for the midterm, it was not, the concept was like the homework. If I did understand the homework, I had no problem, but it's just the time, a lot of people,
Yeah.
there's more homework, problem than what is an exam like.
Yeah, the midterm was a little bit long. So the length of the final exam, we're going to be very sensitive to make sure that there's plenty of time to work out the problems. Yeah. Okay. All right, so let's get back to lecture. So last lecture we looked at PLLs, and let me just remind you of what we were looking at. So basically, you have a phase detector, or more generally a phase frequency detector. Had a filter, and you have an oscillator, and you take the output of that oscillator, go through a string of dividers, and basically you compare the phase of the VCO signal to some reference signal. Okay. And if everything's working well, this is a negative feedback loop, because here you take the difference, you have gain in this loop, and so it's a negative feedback loop, and it locks, basically forces the VCO phase to follow the reference phase, okay, in steady state. So this is the output frequency. Now the nice thing about this PLL, as we talked about last lecture, was that it takes this clean reference signal, which is very stable over temperature, has a very well-known frequency variation is very small, and it forces your VCO to have the same characteristics. So you lock the VCO to a clean reference. Okay? And we're also going to show in this lecture that this loop will actually reject the phase noise of the VCO inside the bandwidth of the loop. So the phase noise characteristics of your VCO will also, in effect, follow the phase noise characteristics of your reference. Okay? Now, if assuming this whole thing works, which is not, it's a huge assumption, then this loop will lock this frequency to this frequency. So we have F output over N is equal to F reference. In other words, the output frequency is N times the reference frequency. And we also talked about the fact that I can make this a programmable divider, in which case if I can change N to N plus 1, then delta F, or the frequency resolution over which I can tune this, is exactly equal to the reference frequency. So in an architecture like this that we call an integer N architecture, where N is constrained to take on integer values, you can switch the channel at the output, you can switch the output frequency by integer multiples of the reference frequency. So usually in those cases the reference frequency is chosen to equal at most the channel spacing, right? The largest we can make the reference in that case is the channel spacing. Yes?
How do you build the frequency divider?
Okay, the frequency divider, we're not going to go into details in this course, but they're actually pretty straightforward digital circuits, so you would have seen them in 141. You basically take latches and use them as delay stages. And so you take, like, just to show you a very simple divider, I would take a D flip-flop and basically, so this is Q, Q, Q bar, take Q bar and bring it into here, and basically clock, bring in my input signal, invert it, and drive another latch. So this is the master latch, this is the slave latch, and this is my output. And what you're doing is, in one cycle, you load up the master latch with, let's say, 1, and the next cycle you transfer the 1 to the slave latch, and then you load up the input latch with the opposite of the output. So this will toggle at a frequency of 1/2 the input clock. Okay. Now, in order to analyze the PLL, we'd like to basically convert it to basically an LTI circuit. And of course, everything is nonlinear in this loop, and this assumption that it's a linear time invariant circuit only applies for if you assume that, let's say, the PLL is already locked and there's a small deviation, or the input frequency or the input phase is very close to the output phase, right? So under those conditions, the equivalent circuit is you have your phase detector, which has a gain, let's say, K sub D. You go through your loop filter, we'll call that G of S. You go through your VCO, and the transfer characteristic for your VCO has some KV. KV controls the output frequency as a function of the input voltage. So to get the phase, we have to integrate. So we see that our VCO characteristics in a phase input, phase output block diagram has a 1/S characteristic. And finally, the divider just takes the input phase and divides it by N. So let me just say a few words about this. So because the phase is omega t, the frequency is the derivative of phase, right? In other words, that phase is the integral of frequency. Or in Laplace domain, it's 1/S, the frequency. So that's why I multiply the output of the VCO by 1/S to get back into phase. So now all the variables in here are phase. So in this case, KV is how many hertz per volt, right? The thing moves around, and then you divide by hertz again, you're back to phase. Okay? Does this block diagram make sense to everybody? Okay, if it makes sense, then we're done, because this is a simple linear circuit, right? And you can use feedback analysis to analyze this. Essentially, for different loop characteristics, you find the poles and zeros of closed loop poles and zeros of the system, and you design it to achieve, let's say, a certain bandwidth. For example, so let's first of all write down the closed loop characteristics of this system. So the closed loop characteristics of the system, let's say H of S, is equal to the forward gain, which is KD KV over S G of S, divided by 1 plus the loop gain, which is the forward gain times the feedback factor, which in this case is 1/N. Okay? And I can simplify this. I can multiply numerator and denominator by S, KD KV G of S, S plus KV KD G of S divided by N. Okay? And so you can see some very simple special cases. For instance, let's say I don't have a loop filter. Okay? If I don't have a loop filter, then H of S just simplifies to KD KV S plus KV KD over N, which tells me that the transfer function is a low-pass transfer function for very small phase deviations at very low frequency. So H of S For very low frequencies, we can see that it just goes to 1. So for low deviations, the transfer characteristic is 1, and the bandwidth, basically the bandwidth over which this loop works, is determined by this pole frequency, right? So the 3 dB frequency is kV/kd divided by n. Now, that's actually kind of inflexible.
One or n, so it goes to one.
This should go, you're right, should go to n. Thank you. Yeah, the reason it goes to n, that's an important point, is because I have a divider in here. So, right, the output phase is basically should go, I'm trying to lock my output phase to be a n times the input phase, right? That's the action of the feedback. Yeah, thank you. The other interesting point here is that the bandwidth is something that I have very little control over. KV is kind of determined by my VCO. Of course, I can design my VCO and change the KV. KD is my detector gain. Again, that's a fixed number. And N is some divider ratio that I'd like to basically set to some constant value. So it's very inconvenient that the bandwidth of this system, there's no knob for me to turn in order to, let's say, improve the bandwidth of the system or to have any kind of control over the phase margin of the system, right?
If you don't put a low-pass filter at the output, will this work? I mean, will this go to the small signal regime so you can start this analysis anyway? Because you have the addition of frequencies as well. You have to cancel that to start this.
Yeah, so it's a good question. So from a linearized perspective, it looks like it'll work, right? But I understand your question. So from a linear perspective, it looks like it'll work. One of the issues is there's going to be parasitic poles that we haven't considered. So these parasitic poles may actually destabilize the circuit. We haven't really analyzed the stability, including the parasitic poles yet. The other issue, as you point out, is that this circuit, if you go in and analyze it in more detail, you'll find that there's many kinds of characteristics that we'd like. For instance, I'd like to be able to change the input frequency, have the output frequency also change. If you analyze these kinds of characteristics, you find that a simple first-order system is not satisfactory, and you have to actually improve the order of the system. So, the next thing you might do is maybe introduce a knob, for instance, introduce a low-pass filter. And again, I'm going to save you guys some time and just write down the result. I can put the result in the following form. Basically, I end up with a second-order transfer function where the natural frequency is omega naught, the 3 dB frequency of the filter, times k square root, where k is the product of kV kd over 2, and the damping factor works out to be 1/2 omega naught over k. Okay, and if you analyze this system, in particular its root locus, you find that basically it does something like this. You have initially two poles. As you increase the loop gain, at some value the poles become complex and they move like so. And as you increase the loop gain more and more, the system becomes wider band but less and less stable. And so again, what you find, for instance, the optimal situation might be to have 45-degree poles or 60-degree poles, or you make a selection. It's just a design of a standard feedback system. Depending on what step response you'd like, you choose your damping factor. Again, though, there is a lack of flexibility here, because once you set your damping factor, again, everything in the system is fixed. And so, apologize because I'm going kind of fast. More than enough details of this are given in your textbook references, so I'm going to just talk about the most common solution. And the most common solution is to use a lead-lag compensation network. In other words, we introduce a pole and a zero in the transfer characteristic. Okay? And this is easily done. For instance, I can make a loop filter like this. Say this is R1, this is R2. This is the input, this is the output. Let's call this C. To prove to you guys that this circuit has a pole and a zero is very simple, because you'll note that at really low frequencies, this is an open circuit, so the output is equal to the input. So I'm at 0 dB. At some frequency, let's say that when this impedance is equal to this impedance, you can see that now I have a voltage divider. So basically, the gain is going to stop dropping. If I go to infinite frequencies, though, this is a short, and the voltage divider degenerates to R2 over R1 plus R2. So at infinite frequency, it flattens out. So clearly, there's a zero and there's a pole. Okay, actually, there's a pole and a zero. Okay? And the effect of this zero is, if we look at the root locus, let's say I put my zero somewhere out here. As I increase the loop gain of my system, as these poles come together, initially they go up just like they do before, but now they bend around, and one pole basically ends up going to the zero, and the other pole ends up going to infinity. And so you can see now I have a lot more flexibility. I can design, basically by placing the zero appropriately, I can play with how much phase margin I have in my system. Okay? From a frequency domain perspective, if you look at it, you have your pole, and basically you introduce this zero, which adds 90 degrees of phase. So it basically allows you to improve your phase margin. So if I look here at my phase, I start out at 90 degrees because I have one pole in the system, a DC pole, and my phase margin now goes to 180 degrees because of the presence of this pole, and then this zero brings me back down to minus 90 degrees. Okay? So this greatly improves the stability. Without this zero, I would have to make sure that the loop gain drops to 1 before I hit this 180 degrees. Now I can actually make the system wider band by introducing this zero. Okay? Alright, so you guys are going to have some fun with PLLs in this homework. Let me just say a couple of interesting things about the PLL, just to summarize. One of the most important characteristics of the PLL is that if I look at the transfer function from the input to the output, obviously it's going to be some low-pass characteristic. So for instance, if I have noise on my reference, the transfer function is something like that, where this is the pole frequency. There's some peakiness depending on how much damping you put into it. So high frequency noise gets filtered out nicely. If I look at the transfer function though from the VCO port, so if I assume that my VCO, instead of being a perfect VCO, has noise characteristic associated with it, phase noise, then the transfer function looks something like this. It's a high pass transfer function, which means that very high frequency noise in the VCO will actually make it to the output, but low frequency noise gets filtered. Well, that's great. That's exactly what I want, because remember, the VCO can be represented as an ideal VCO with a delta function plus phase noise. And that phase noise is very low frequency. It's very close to the carrier. So noise close to the carrier will get filtered out by my PLL. So if I look at the overall phase noise of my system, it might look something like this, where this is the bandwidth of the PLL. This is the phase noise of the free-running VCO. and you can see it's been suppressed by the loop gain and flattened out. And then this is my out-of-band noise is mostly dominated by my VCO again. Because the filter can't filter out this component of the noise. It's outside the bandwidth of my system. Now so this is a phase noise. If I look at the voltage spectrum at the output, it'll look something like this. Where, let's say this is the original free-running VCO. And now, the closed-loop VCO characteristic inside the band, again, the phase noise has been suppressed. And then the outside the band, the phase noise is just determined by the VCO. Okay? So this is why when you design a VCO, the far-out noise is also very important, because the far-out noise is going to be dominated by the VCO itself. It's not something you can correct. Okay? Now, phase lock loops, there's a lot more we could talk about, but I'm going to leave it at that, and you guys will do the homework problem, and you'll get a better idea of how to control the loop dynamics in the homework. What I want to get to with the next topic, which is quite important, is power amplifiers. Okay. Right. Any questions before we do that? Yes.
Inside the bandwidth, the phase noise is suppressed. Is it because that it locks to only the VCO frequency? So why is it suppressed within the band?
Well, you can model. So let's come back here. Okay, so this is a ideal VCO, right? So I can model this, the phase noise of the VCO, as basically a source here that introduces noise into my system, right? So then I could write the transfer function from here to the output, right? And I find the transfer function is high pass. That means that the phase noise of the VCO is getting suppressed by the loop, because the loop is trying to lock on to this signal. This signal throws it off, and so then the loop will correct for the noise injected at this port. As long as this noise is very low frequency, this loop can correct for it. Right? That's right. Remember, phase noise at low frequency corresponds to close-in phase noise. Yes?
So along this line of thoughts, so that's true that for PL designs, the loop of PL loop should be faster than carrier frequency. And for direct conversion, it should be faster than baseband. For two-step, it can be faster than intermediate band.
No, so the loop bandwidth here, there's basically a trade-off between the reference frequency and the loop bandwidth. And what you find is that you can't make the loop bandwidth very large when you design these things. Okay? I'll give you an example. The loop bandwidth might only be 20 kilohertz for a PLL. And the reference frequency basically might be 200 kilohertz.
Voice signal frequency.
Well, remember, there is no, at this point, in this discussion, we're not using this PLL to do any kind of modulation. All we're doing is we're trying to lock it to the input phase. We're just taking the phase as a reference, this crystal as a reference, right? This might be a crystal. And we're trying to lock the output of the VCO to this crystal. So the bandwidth, the only time the bandwidth comes into play is if I want to switch frequencies. So if I want to go from frequency 1 to frequency 2, from n to n plus 1. The settling time of this loop then is determined by the bandwidth. So the higher the bandwidth, the faster it can settle, right? So from that perspective, we'd like the loop to be very fast, but we have this trade-off, because if we increase the bandwidth, right, basically we can increase it the reference frequency more or less determines what the bandwidth of the loop is going to be. Okay? Okay, so let's talk about power amplifiers. a lot of our discussion will be quite general. You know, a lot of times here we emphasize communication systems, but there are many places where you need power amplifiers. So a power amplifier, very generically, you apply some input power, it delivers some power to the load. Let's say the load is 50 ohms, or it could be 100 ohms, or 75 ohms, or kilo ohms, depending on the application. Many applications that we think about driving antennas, so the impedance is actually quite low. The power amplifier also consumes power from the DC supply, okay? And it basically generates heat. Of course, this is undesirable. So what's really important about a power amplifier is what we call the power added efficiency. In other words, if I look at the power that actually gets the load, if I subtract how much power I'm putting in and divide it by the total DC power consumption. So clearly, by conservation of energy, this DC power is supplying this difference. So this is less than or equal to 100%, right? Assuming that this is only connected to one source of power, DC power, and the DC power is coming in from here. Unfortunately, you'll find that it's really hard to design an amplifier that approaches 100%. In fact, you might say, well, what's so special about power amplifiers? Why can't I just take, I don't know, an inverter and use it as a power amplifier? Okay, I think it's a good exercise for you guys to take an inverter and connect up a 50 ohm load, deliver, let's say, some amount of power, 100 milliwatts or something, and then see what your efficiency is. And you'll find that the efficiency is actually a few percent, which is very wasteful, right? That means that most of the power, instead of going to your antenna or to your speaker or whatever this happens to be, most of it is just going to heat. Okay, so you're not doing anyone a favor. You've built yourself a mini heater. You haven't built yourself a power amplifier.
Question. So since you're driving you're swing the loads in an antenna, this power amp has to be a very linear circuit?
We'll talk about that later. So in some applications you can tolerate very nonlinear power amplifiers. In others, depending on how much amplitude modulation you have, you can tolerate different levels of linearity on the PA. So we'll come back to that. All right, so again, power amplifiers are not just for communications. Let's look at an audio power amplifier as an example. So let's say that the load is a 1 kilo ohm speaker. I'm sorry, an 8 ohm speaker. And let's say we want to deliver 1 kilowatt of power. Okay? Say, you know, over the weekend you want to boost the power in your car stereo. You want to play music really loud. All right, so first of all, what's the voltage? How many volts do you have to swing over 8 ohms to generate 1 kilowatt? So V squared over 2R is equal to PL. In other words, V is 2R PL square root. In this case, we have 2 times 8 times 1,000 square root, or about 126 volts. Okay? That's a lot of voltage, right? Car battery is only 12 volts, right? So you're going to have to do something special to get up to 126 volts. Well, that's not a problem. Maybe we can use a transformer or something. How much current is flowing? Well, the current is 2P over R, 2P over V, excuse me, and that works out to be about 15.8 amps. Okay? So now you can appreciate how difficult it is to deliver power. The voltage is really high and the currents are really high. You know, 15 amps, you know, forget using a tiny little integrated circuits, right? That little inverter that we talked about, to be able to put this much current through an inverter, you'd have to make the aluminum wires so wide. The rule of thumb, on-chip wires, the maximum current density you can put is about 1 milliwatt per micron, right? So to get 1 watt would require 1,000, so you'd need a millimeter wide wire, and to get to this level you'd need basically very, very hefty, thick wires, in which case you'd have so much capacitance that the 3 dB frequency would be extremely low. Okay. Obviously, to deliver this level of power, you're not going to use a normal integrated circuit. You're going to use power transistors. All right. So let's look a little bit more at efficiency. So the power added efficiency, as we defined, is the power of the load divided by the power of the input divided by the DC power. And the power that goes into your PA, of course, is just the power of the load divided by the power gain of your PA. So if I substitute that here, that is basically, I can write the PAE as PL 1 minus GP inverse divided by PDC. And I give a special name to this quantity. I call this, for historical reasons, the collector efficiency, the power of the load divided by the DC power. So the PAE is the collector efficiency times 1 minus inverse GP. Clearly, if you've got a lot of power gain in your device, this term goes to 0 or to 1, and so the PAE is really just your collector efficiency. If your power goes really low, for instance, if the power gain is just 1, PAE is 0, right? The efficiency of the system is 0. You're not basically adding any power to the input signal. So this PAE is only different from collector efficiency when, let's say, GP is not substantial. Okay. All right. So we looked at the audio example. Let's look at a cell phone kind of example. So in a cell phone, let's say I want 1 watt of power to go into my antenna. Okay, that's actually a pretty reasonable number for a cell phone. How does that translate? Again, in terms of the voltage swing, how many volts is that into 50 ohms? Let's say my PA drives a filter, and the input impedance of my filter is 50 ohms. So from the PA's perspective, it sees a 50 ohm load, and it needs to deliver 1 watt into that load. Let's assume this filter is lossless for the time being. So again, using 2πr square root, that's square root of 100, or exactly 10 volts. So I need to swing 10 volts on 50 ohms. How about the current? Well, the current works out to be 0.2 amps, okay, or 200 milliwatts. So now the numbers are more reasonable, but again, they're not trivial. 10 volts is not trivial. If you use a modern process, a breakdown voltage, let's say 90 nanometers, 1 volt. So how do you swing 10 volts? You need to, basically, you can't ever expose this voltage to any real device. It would break down. If you go to older technologies, you can certainly have technologies with breakdown voltages over 10 volts, and so this is less of an issue. Then the current becomes an issue, right? So, in fact, I think, yeah, let's look at this a little bit more detail. So, let me assume that I use a transformer so that I don't expose my device ever to that 10 volt. Okay? Let's say I decide that I can handle up to 2.5 volts. Let's say it's a 0.35 micron process, and I'm pretty safe with 2.5 volts. So basically I use a 4-to-1 transformer, and everything looks great, except remember this was 0.2 amps. Well, what's this current now? 0.8 amps, right? So I've translated the problem. Now voltage is not an issue, but current is a huge issue. Okay? Why is current such a big issue? Why can't I use large values of current? Heating? Yeah, I mean, one way to look at it is, let's say that you lay out this device, and in your layout you end up with 1 ohm of parasitic resistance. Okay? So the power loss through that device is 1/2 I squared R, and that works out to 0.16 times 1/2 or 0.08. Let's see, 0.8 is, 0.64. Yeah, 0.64. So this works out to 320 milliwatts. Yeah. That's a lot of power, right? I'm delivering only a 1 watt to my load. All of a sudden, I'm losing 300 milliwatts to this 1 ohm series resistance. You know, that's pretty bad. And you know, you might think of 1 ohm as a small resistance, but 1 ohm has basically killed your PA. Whatever efficiency you had, your efficiency is degraded substantially. So clearly, one of the difficulties with this PA is you've got to make sure there are no series resistances. Transformer? Well, yeah, transformer has winding resistance. So that's going to destroy your efficiency right there. You lay out transistors, you have interconnect, you have resistance, you have the interconnect to get to the transistor. You have to make sure that those resistances are extremely small. So it is very challenging to work with high currents. Okay, the other issue is power loss. So let's assume that you basically have to live with this 1 ohm resistor. And so let's look at how that impacts the efficiency. Okay, so the power loss now is 320 milliwatts due to that resistor, plus the power that you're losing to your PA, which is, again, assuming a high value of gain, that's just PL over the efficiency. This works out to 2.32 watts. Okay? In which case, if I now calculate the efficiency, I'm delivering 1 watt to my load, and I'm burning 2.32 watts. In other words, my efficiency is 43%, assuming I started out with 50% efficiency. Okay? So you worked really hard to produce a PA with an efficiency of 50%. Somehow you end up with 1 extra ohm, your efficiency drops by 7%. It's pretty dramatic. You know, and if you go and lay out a board, you can see that 1 ohm is not too hard to get. For instance, one place you might not expect it is the transmission line. So you have your PA, it drives the transmission line, and then it goes into a filter, and then it goes into your antenna, and you have a connector here. So these transmission lines will introduce insertion loss. This filter will have a loss. And so basically what you find is that designing a PA, you have to be careful that you always think of how much power gets the antenna and count all the losses incurred while getting to the antenna. Going back to our example, if I assume that this transformer has 2 dB insertion loss, which is actually quite typical if you put this transformer on chip. 2 dB corresponds to a gain of 0.63. In other words, only 0.63 of the power that I put in on this side makes it to this side. So the efficiency is 0.63 times power to the load. Total DC power, using the same example, plugging in the numbers, the total efficiency now drops to 24%. So remember, we start out with 50%. We took into account the small little resistor and this transformer, and we're down to 24%. Okay. Okay. Let me stop here and take any questions.
Are power amplifiers usually on chip or off chip?
Power amplifiers, it depends. Depends on the power level. So if you're talking about commercial products today for cellular phones, power levels on the order of a watt, most of them are PA modules. So you have one chip, inside it you just have transistors. And those are high voltage transistors. They can handle high breakdown voltage. And all the passive elements are actually integrated into a module. So really it's not on chip. If you go to lower power levels, say hundreds of milliwatts for, say, wireless LAN, or tens of milliwatts, then the integration is actually possible and desirable. There are, there's research, there's also some companies that are trying to put the whole PA on a chip, but you're never going to get the efficiency levels that you can using an off-chip modular solution. So you can put it all on chip, it's just your efficiency is going to suffer. All right, so some of the issues, let me just summarize some of the PA issues. Okay. So as we've seen, PAs basically drive large voltages and large currents into basically relatively small impedances. And so what we find is that any loss basically in series or in shunt, should actually put them the other way around, hurts. Series losses because of high currents, shunt losses because of high voltages, right? Heat generation is a huge issue. So if I have a 1 watt output and my efficiency is 50%, that means that the DC power consumption is 2 watts, right? So I'm basically turning 2 watts of energy into heat. So really you need to provide heat sinking, basically good packages, good thermal packages. And you need to manage basically, you also need to watch out for thermal stability. In other words, some transistors, in particular bipolar transistors, the hotter they get, the smaller the VBE gets, and so the higher the current. So on its own, if you don't do anything about that, the transistor will run away thermally. Its current will keep increasing until it destructively breaks down, melts. MOSFETs, fortunately, have a negative thermal coefficient. So as the higher the temperature gets, the VT shift causes the current to decrease, and so thermally they're stable. So another important consideration for PA is the packaging, because basically a PA interfaces to the external world. In this class we've talked a lot about receivers, and the receiver is kind of internal. You take the signal from the outside and then you do something with it inside. PA though has to drive something that's outside, and so the package parasitics play a very important role, because that's how you get your signal from the chip to the outside world. You have to go through your package. Finally, because a PA transmits a lot of power, any kind of spectral leakage basically can act as interference. So for instance, if I have a PA and it's connected directly to the antenna, let's say this is my input power, and let's say this is the input, this is the output, and then these are my harmonics. So my second harmonic, my third harmonic, these things are falling into potentially other people's spectrum. So basically this is someone else's backyard, so to speak. More importantly, what you find is that you get also problems with spectral regrowth. So let's say this is my input spectrum. The output spectrum, of course, is bigger because the signal is gained up, but you find that you have spectral regrowth. In other words, the nonlinearity in the PA causes the spectrum to grow. And then you have leakage into, let's say, a neighboring channel. So this is, let's say, a weak neighbor. These guys are distant neighbors. Maybe you don't care so much about your distant neighbors. It's hard for them to find you, but your near neighbors are going to find you. Okay? And, all right, so these are kind of a quick introduction to the overview of power amplifiers and some of the issues. Now we're going to look at specific implementations of power amplifiers and what kinds of efficiencies we can achieve, what kinds of linearities that we can expect. Okay? Any other general questions about PAs? Okay. Frank, do you have any questions? Okay. Let's look at an emitter follower. Okay. We kind of like emitter followers, right? Whenever you talk about driving an offload stage, you say, emitter follower, nice. Because an emitter follower has low output impedance, it has good distortion characteristics, right? This acts like degeneration, so it has very good linearity. So I'm going to apply my input signal, and this is my output signal, and we know that there's quite a bit of power gain in an emitter follower, even though there's no voltage gain. Okay? So the question is, what's the efficiency of this guy? All right? So let's start out and just calculate the power that I get at my load. Well, let's say I get a swing of V out at my load. That's the power at the load. What's the DC power consumption? Well, that's easy. I'm holding this current constant. There's no DC current going through this cap. So the DC power consumption is, let's say, VCC times IQ. And so my collector efficiency, really should call it the emitter efficiency, but we'll call it that, is given by 1/2 V out squared over RL divided by VCC IQ. Okay? And you'll notice that the current I out is just V out over RL. So I can write this as 1/2 V out over RL, 1 over IQ, V out over VCC. And if I substitute for I out, I have the following equation, which is 1/2, let's say, the normalized current times the normalized voltage. Okay, so this is an important equation. We can, for almost every amplifier stage, we can put the efficiency into a form that's some constant times normalized current swing, normalized voltage swing. Okay? So the observation here is, obviously, we'd like to maximize these quantities in order to maximize the efficiency. Okay? So, basically, to maximize efficiency, we maximize V and I. All right? So right off the bat, you note that V and I are not independent. I can't just independently increase I and V because I and V are locked by this relationship. So the first thing you say is, wouldn't it be nice if instead of driving RL, I could drive some other impedance? In other words, sure, I can do that. I can transform this impedance to any convenient value. Right? So in other words, RL, which is V out over I out, I can always change this to basically a more convenient and I'll say more about that as we go on, but the important point is that if in my emitter follower I were to add a matching network, assuming this matching network is not lossy, then here I could see RL prime, where perhaps RL prime can give me better efficiency. The idea here is that if here these are two dependent variables. Now by making this RL prime, I can change these independently. Okay. All right, so let's look at what kind of current swings we can get out of a emitter follower. So the important observation about an emitter follower is that the current I can deliver is virtually unlimited. As I increase this voltage, the output current increases, and that's delivered by my device Q1. So this device delivers IQ plus I out. And I out can get as large as you want as long as you don't melt this transistor. So on the positive side, there's no limitation to the current swing. So if I were to plot, let's say, the total output current, let's say ICC, the DC value, of course, is IQ. I can also easily swing about this. If I increase my input voltage, no problem. It keeps doing this. If I increase it a lot, I can get really high values of positive current, but you can now see the problem is that I have only a limited amount of negative current I can supply before the system clips. Okay? And as soon as clipping happens, all hell breaks loose, because now the output current is not linearly proportional to the input voltage. And so the linearity relationship is no longer satisfied. Now, how large is this negative swing? Well, obviously, it doesn't take a genius to figure out that it's just IQ. Okay? So the I out, because of the negative swing, has to be less than IQ. At best, it's going to equal IQ. All right? That means that my normalized current is necessarily less than 1. Okay? Questions? Okay, how about the voltage swing? So let's call this slide current swing. Let's call this slide voltage swing. Okay, so what's the largest value I can take this voltage? So if I'm plotting, so let's say this is VQ, that's the voltage here. As I basically increase the value of the input, the output also follows in step, but clearly it can't go too large, right? Because if it gets too close to VCC, this device will go into saturation, right? So on the positive side, I can only go as large as VCC. Similarly, on the negative side, this is a current source. It's not in reality, it's never an ideal current source. It needs a little headroom to stay alive. Let's say a headroom of about VCE sat. So minimum, so VQ max is roughly VCC minus a saturation voltage. VQ min is also at least a VCE sat of this transistor. So the best I can really do, so if I were to design the system, the best swing I could obtain would be if I biased VQ at mid-rail. Let's say this is VCC, this is 0 volts, and I basically swing around this mid-rail point, where this is my kind of boundary over which I can't go larger without introducing significant distortion into the circuit. So if this is the maximum voltage swing I can have, you can clearly see now that the swing is at most half of VCC. In other words, V out is, let's say, less than VCC over 2. And again, an upper bound, therefore, for the normalized voltage swing is 1/2. Okay? Any questions about that? Alright, so now that we have our normalized current and voltage swing, we plug in, we found that this is at most 1, and we found this is at most 1/2, which tells me that an upper bound on the efficiency of this amplifier is 25%. Okay? More realistically, let's say that VCE SAT were about 300 millivolts and VCC were 3 volts. Then you'll find that the efficiency is more like 20%. Okay? That means that 80% of the power is getting wasted, turning into heat. It means if if you try to put this into a cell phone, 80% of the power is kind of heating up your head or your hand, and the rest is making it to the antenna. It's not a really nice situation. It's kind of shameful as an engineer to say that your power amplifier is only 20% efficient. Actually, we'll see that it's pretty hard to do. Depending on your linearity requirements, 20% is actually not a terrible number. You shouldn't go crying home if you get an efficiency of 20%. But we can do better. So we're going to talk about how to improve this efficiency. All right? Well, let's look at other topologies. For instance, if we had a resistor that we could bias relative to VCC, you might try a topology like this. Okay? And again, we don't need to do much math, so this is a common emitter amp. We know this has good power gain. We know it has relatively good frequency response if basically this Miller effect doesn't hurt us too much. But forget the frequency. Let's just focus on efficiency. You guys all know that the situation is very analogous to the common emitter amplifier because I biased this up with some current IQ. Now the transistor current can't go below cutoff, right? Can't go below 0. And so again, my current swing is less than 1. And the voltage swing, again, the same argument. On the low side, I can go as low as VCE SAT. On the high side, I can go all the way to VCC now, when the current drops to 0. So at this point, when the current is dropped to 0, my output can get as high as VCC. When the current peaks, though, I can only go down to about a VCE SAT. So again, you can see that the voltage swing is also at most 1/2. It's really VCC minus VCE SAT divided by 2. So plugging in the numbers, again, we get the efficiency is at best 25%, which is not that satisfying, right? But you got to live with it. We also didn't say what the optimum load is, so let's talk about that. Okay. So in doing all this analysis, we assume that we could choose the voltage and current independently. In reality, though, the load that we'd like to see is V out over I out, which is normalized V over normalized I times VCC over IQ. And so now you could see that if the normalized voltage swing is 1/2, then and let's say the normalized current is 1, then the optimum efficiency is the optimum load to achieve that high value of efficiency is 1/2 VCC over IQ. Okay, and again, you can't arbitrarily choose IQ because you need to. The power of the load is 1/2 I out squared RL. This is the real load, not the loads. So let's say this is the load of the amplifier before I transform it. So this is the load, transformed load, in other words, which is equal to R opt. And so you can see now that if I have some kind of matching network, let me call this RL prime and this RL, I can transform this RL to this value of RL prime, which is this optimum impedance, which basically the value of which is given by how much power you want to deliver to this load. Okay? Alright, so even with this matching network, the best we can do is 25%. And if you actually calculate the value of R opt, what you find is if the current is relatively high, this resistance value turns out to be very small. Let's just do a quick example. Okay. All right, so let's say, let me use an emitter follower. Okay, let's say I want to deliver 1 watt of power. Okay? And that's equal to 1/2 V normalized I normalized times VCC times IQ is equal to 1 watt. And let's say here this is 1/2, this is 1. Let's say VCC is 3 volts times IQ has to equal to 1 watt. So that means that IQ is 1 divided by 3 times 4, or about 1.33 amps. Okay? And R opt is equal to 1/2 VCC over IQ, which is 3 divided by 4 times 3 times 1/2, or 9 over 8 ohms. Okay? So about 1 ohm. That's pretty hard, right? So if this is 50 ohms, that means my matching network has to take 50 ohms down to 1 ohm. And if you guys remember when we studied matching networks, we found that the insertion loss of a matching network is proportional to the matching ratio. So here we need a matching ratio of 50 to 1. So that means that the quality factor of the components we use in this matching network has to be very high. In fact, it has to be much higher than square root of 50. So it's not trivial to just take this from 50 down to 1 ohms. We're going to get quite a bit of insertion loss in this matching network. All right, questions? Yes?
For the common emitter amplifier at least, can you put an inductor in parallel with RL to increase the swing on the voltage?
Sure. So in fact, that's the next slide. So if we look at an inductor loaded amplifier, let's say for now we'll just put an RF choke so it doesn't affect the frequency response at all. These are all ideal. Put a big capacitor in series and we put our optimized load here. Okay? So now what we find is that V out can approach 1 as opposed to 1/2. So let's see how that happens, okay? So the DC operating point now here is equal to VCC because for long time periods, right, this just acts like a short. It shorts this point to VCC. Now what's kind of weird here is, first of all, what happens is I increase this input voltage. Well, as I increase this input voltage, because of phase shift here, this voltage goes down, goes below VCC. In fact, it can go all the way down to VCE sat, just as before. What's weird is now what happens when I decrease the input voltage. That means the output voltage is going above the supply voltage. So now I find that I can swing this point all the way above VCC up to twice VCC, in fact. Okay? And the reason that that happens is because this is an inductor. So an inductor, the voltage across the inductor is proportional to the rate of change of the current. So if the current is changing, increasing, the voltage across the inductor will be, let's say, like that. If the current decreases, though, then the voltage sign across the inductor flips, and this point goes VCC plus VL. And VL can be as large as VCC, giving us a voltage of twice VCC at this point. Okay? So one way to understand what's going on, if this really bothers you, is to look to see what's happening at that point. At that point, this output resistance, RL, is at VCC. And this bypass capacitor is also charged to VCC. And this voltage across here is also VCC. So that tells you that from the supply voltage across the inductor, I'm at twice VCC, and then this bypass capacitor drops me down to VCC, and then now I'm swinging VCC relative to ground across this load. Okay? So this is really nice. Let's draw a picture of it. This is basically the quiescent operating point, which is VCC, and the idea is that I can swing the voltage above and below supply and end up with a much higher supply swing at this point. Again, if this thing bothers you, I have another way of looking at this which may help you. Think of an inductor. Inductor likes to see a zero average voltage across it, right? DC voltage across the inductor, ideal inductor, should be 0. So if I swing below VDD here, in order to maintain an average value of VCC, this voltage better swing also above VCC so that the average works out to VCC. Okay? If you think about it that way, in fact, next lecture when we look at switching amplifiers, you'll be able to very quickly understand the voltage waveforms on a switching amplifier. Alright, so now, because I can go as high as VCC here, this can go as low as VCE SAT, or if we're talking about MOS devices, a VD SAT, and I can go approximately to twice VCC, you can see that normalized voltage swing is now 1, so my efficiency is 1/2 V times I. Both of these now are 1, so I can hit 50%. Okay. Questions? So, pretty nice. By just putting an inductor here, this might be an RF choke, we've gone from an efficiency of 25% theoretical maximum efficiency to 50%. We doubled things, just one inductor. From a stress perspective, though, we've put more voltage stress on this device because now the voltage swings as high as 2 VCC. So I have to make sure the breakdown voltage of this device, the RF breakdown voltage, is at least 2 VCC or better. So if this is a 3-volt supply, I better use a transistor that has a breakdown voltage around 8 volts to have a little bit of margin. Okay. Now, one of the nice things about this choke inductor is in real life you probably won't use a choke. In real life, choke being a large inductor, in real life your device has some output capacitance, some parasitic capacitance, and I can use this inductor to supply here to resonate out this capacitor. And so now, looking out here, I hopefully see a very high impedance. I see an inductor in parallel with a capacitor in parallel with the output resistance of this device, which is hopefully pretty high. And so this circuit, let's call this C-par. This circuit now resonates, and I have a tuned amplifier. Okay. In this case, if I use a very large inductor, this works very well down to very low frequencies. Basically, the R over L is the cutoff frequency for this. So the price I pay here is I turn this into a tuned amplifier, but I can operate at much higher frequencies. Okay? And in fact, if I have a 50 ohm load, I want to impedance match it down. So for instance, I can use an L matching network like we did before when we talked about LNAs. So here I see a low impedance. Questions? Comments? All right, so looks like, you know, designing something like this could get us close to 50%. You know, worst case scenario, we could put these things off chip. Remember, this has a large matching factor. You know, this might be on the order of an ohm. So we would like to use very high Q components. So here we're going to use high Q components. And they'll be off-chip components. Let's say the quality factor is 40 or 50 or something really good. We're willing to pay for it because this is very important. It impacts our efficiency. Because the voltage, basically what we've done is we've taken a high voltage swing on the order of 10 volts here and converted it to a lower voltage swing on the order of VCC. And so the price that we've paid is current. Now the current swing is very large. And of course, the current swing goes through our device, right? That means our device has to be able to handle a very large current. Let's say on the order of an amp of current for a 1-watt system. And that means this device is going to be very large. So one of the issues with PA design is that this is a very large device. So what are some of the negative effects of using a very large device here? Capacitance, yeah, we talked about that. So this device will have lots of capacitance, feedback capacitance, output capacitance. Hopefully, we can tune out some of this capacitance. Okay, and note it's not so easy to use something like a cascode, because a cascode will even reduce our swing more. Right? The swing here is very important. What are some of the other issues with using a very large device? Yeah, very good point. It's hard to drive a large device. That's a very good point. It also has lots of parasitics. What other negative effects does it have? Okay, ballasting, we'll talk about that a little bit later, but stability, thermal stability issues, right? And what was the first thing you said?
Current sharing.
Okay, yeah, okay. Current sharing, ballasting. Yeah, that basically, if you're using a bipolar transistor, it goes back to what we said earlier. As this thing heats up, it could thermally run away. The current actually, we'll talk about that next lecture, so let's not, I'll draw a nice picture for you. Okay. One more thing I want to hit before the lecture ends. What's another negative effect? Think about this load. It's 1 ohm, right? Okay, so matching. We didn't say anything about impedance matching, right? In fact, we've purposely mismatched our power amplifier. If I impedance match, let's say so the output impedance of the device is 1 ohm, how does that impact my efficiency? It kills your efficiency, right? Because now half your power is getting lost in the output impedance of the device. So we purposely design PAs so that there is a mismatch. In fact, we'd like the output impedance to be much larger than the load impedance. Okay? And so the other issue that happens is if we make this device too big, its output impedance starts to get small, comparable to this load impedance that we're trying to drive, in which case we get less efficiency out of the PA. Okay, we'll stop there and pick up next lecture.